Hello everyone. This pre-lecture I want to talk about a really interesting application of magnetic fields, and we'll get some electric field application in here as well. It's called the Hall effect. So this is section 28.6 in Survey, and it's a really nice review of electric fields, electric potential, and also including some applications of magnetic fields. So that's why it's a really nice application to kind of refresh all of the concepts that we've been talking about in this course. And it's also really useful. Every probe that you use to measure magnetic fields uses the Hall effect. So after this lecture, I'm hoping that you'll understand what this thing that I'm calling the Hall effect is and why it's useful. And mostly I want you to understand the qualitative story about why this Hall voltage is developed and how we measure it. Okay? And hopefully you'll be able to determine the magnitude and the sign of the Hall voltage for a given setup. Okay? And this Hall voltage can be used to determine all kinds of properties of your material or of your lab setup. For example, if you don't know a magnetic field, you can use the Hall voltage to determine it. That's the most common application, that you can create a probe which will measure the magnetic field using the Hall voltage. You can also learn about properties of materials, like how dense the charge carriers are in the material, or how fast the charges are moving in that material using the Hall voltage. So here's the setup. The idea is basically you have a current flowing through a conductor. So this blue chunk here is a conductor. I'm passing a current through that conductor. You can see I've got it hooked up to a battery here. And so the current is going to go, in this case, from plus to minus. So the long side is the plus, the short side is the minus. And so I'll have a current going this way in the circuit, right? So my current is going this way, and we'll come back this way. Now I'm going to take this, this apparatus, and I'm going to put it into a magnetic field, okay? So you can see that there's a magnetic field pointing into the page here. So what's going to happen, you've got charges moving, and then when they enter this magnetic field, they're going to get pushed around by the magnetic field. So let's suppose, once again, remembering that the current is this way, but remember that current is the direction of flow of positive charges, right? So that if electrons are carrying the current, they're going to be moving in the opposite direction of the current, of the conventional current. So if electrons are moving through this conductor, the blue chunk there, they're going to be moving to the left. Right? The velocity of the electron is given by that red arrow, just moving to the left there. And now the magnetic field is pointing into the page, so now you have to think about what's going to happen to that electron. If it's moving through that magnetic field, it's going to get pushed around by the magnetic field. Which way is it going to move? So maybe you can take a moment, pause the video, and see if you can explain which way that electron would move in response to the magnetic field pointing into the page. Hopefully you got the answer that it points upward. So if you take the fingers of your right hand using your right hand rule, and you're pushing them in the direction of the velocity. So my fingers of my right hand are in the direction of the velocity. Now I need to curl my fingers in the direction of the into the page. Okay, so that's like this. Fingers in the direction of a V, curling them into the page. I get my thumb pointing down. But remember, that's the force on a positive charge. So if it's a negative charge, electron in this case, I have to flip it by 180 degrees. Don't forget to flip it over 180 degrees if you have a negative charge. That force is upward, so that electron would get deflected upwards because of the magnetic field. So initially, these charges, which are moving to the left, are going to get pushed upward to the top of this material because of the magnetic force. So you should envision, I've only drawn one charge here, but you should envision a bunch of charges carrying the current. There's a ton of charges moving this way, and they're all getting pushed upward towards the top of the material by the magnetic force. And what's going to happen is you're going to get a buildup of charges on the top of this material. So there's going to be a bunch of electrons which are going to be moved up here. They've gotten pushed up to the top because of the magnetic force. But then the more charge you get built up on the top, you're going to be repelling other electrons away from you. So you see there's a competition going on. The magnetic force is pushing the electrons up to the top of the material, but then as more and more electrons build up on the top, they're going to repel other electrons from coming. So you see there's going to be a balance that's struck, that eventually I'm going to have so many electrons built up at the top that I won't have any more that will get pushed up. That way they'll be repelled by the existing electrons. Okay, so this is what you should envision, a bunch of these charges, all of them getting bent up to the top here. And so you have a ton of electrons up at the top. And you can see that the top surface is going to become negatively charged because of this buildup of electrons. Okay? And then I've drawn that the other surface is going to be positive, and that's because the whole chunk of metal is neutral. If I push all the electrons to one side, the other side will be positive, right? I have to have an equal amount of positive and negative charge in this material. So if all of the electrons are on the top, the bottom will be positive because there's a lack of electrons on the bottom. Okay? So I have created this separation of charges. I've created a negatively charged plate. It's like a surface at the top, which is negatively charged, and a positively charged surface at the bottom. And you know what happens when you have a separation of charges. So I have plus charges on the bottom, minus charges on the top. I have an electric field, right? An electric field points from plus to minus. So positives on the bottom, negatives on the top. There's an electric field which is developed in this situation. Okay, so take a step back, make sure you understand this story. The current is being carried by electrons. The electrons are getting pushed upward by the magnetic field. That means that I end up with negative charge on the top of the material, positive charge on the bottom. There's an electric field which is developed in the material, which is called the Hall electric field, named after Edwin Hall, who's the one who discovered this effect. So EH is the Hall electric field. That's the field which is like developed because the charges moved in response to the magnetic field. Okay? So two things going on. Magnetic field is pushing the charges around. Because the charges get pushed around, they've separated the positives and the negatives, and you have an electric field which is developed. Okay? Now this electric field, you know that electric fields point from high potential to low potential. So that means, I have a bunch of positive charges at the bottom here and a bunch of negative charges at the top. That means the bottom of this material is a higher potential than the top of the material. And if I hook up a voltmeter to the top and the bottom, it will measure a difference, a potential difference between the two sides of the material, and that's what we call the Hall voltage. So that's what's shown in this diagram here. This is basically the same diagram, but just taken from the textbook. You've got positive charges on the bottom, negative charges on the top, magnetic field is pointing into the page, and then you connect a voltmeter, which is here, to the top and bottom of this material. The positive charges are like hills, right? Those are higher potential. The negative charges are like the valley. Those are lower potential. If I hook up a voltmeter between the two sides, between point A and point C, there's going to be a potential difference between those two. This voltmeter is reading a negative voltage. What does that mean? It means that the thing connected to the positive, which is point C, is 1.5 volts below the thing connected to the negative. Okay, so this voltmeter, when it's hooked up this way, it reads a negative voltage. That's telling you that the top surface of this is at a lower potential than the bottom surface. So in a real material, of course, you can't see the electrons moving, but you can hook up a voltmeter to the two sides and measure this, and that will tell you what's going on inside the material. Now, like I mentioned, there's going to be this competition between the two forces. Basically, you have the magnetic force, which is pushing the electrons upwards. That's why the top surface became positive initially, because of this magnetic force. So you can see it here, QV cross B. But then there's a competing electric force, which is, repelling this electron that's drawn in this diagram is being repelled downwards. And eventually those two will come to balance each other. So initially, there's no charge on the top, right? At the very beginning, there's no charge on the top. And then the charges get pushed up there by the magnetic field. But then eventually more and more charge builds up on the top, and that will counteract the initial magnetic force, right? And so a balance is struck where the magnetic force upward is going to be balanced by the electric force downward. And then everything comes to equilibrium, and there's no more buildup on the top, right? It's sort of the buildup stops, and this voltage here will stabilize. This all happens very, very quickly in the span of, a nanosecond or so. So when exactly does this stop? In other words, like, what's the magnitude of this electric field which is going to cancel out the magnetic force? It's going to happen when these two forces balance each other. So the key part is that the magnetic force upward will eventually be balanced by the electric force downward. So there's going to be enough charge on the top surface of this material to cancel out the magnetic force upward. When does that happen? That happens when those two forces are equal. So that happens when you have QE, which is the electric force downward, is equal to QVB, which is the magnetic force upward. And of course the Q's cancel out here. And I get that the electric field which I develop is equal to the magnetic field times the velocity of those charges. Now, how is this related to the voltage that you measure? Remember that the electric potential, delta V, in a uniform electric field is the magnitude of the electric field times the distance that you've traveled in the direction of the field. Maybe I'll put an absolute value on this. So if I go from one side of this material to the other, like down here, the distance which I've traveled is what I'm calling d. So this d here is this width of this material, is the dimension of the material in that direction. So that means that the voltage difference between the two sides is the magnitude of the electric field, E, times the distance between the two sides, which is what I'm calling d. That's this relationship here. Delta V is equal to E times d. The last step is to substitute in for E. I'm going to substitute in V times B. Okay. So I took this equation here and substituted into the third equation to get the fourth equation. So this equation is very interesting because if you think about it, you measure this, right? You measure the distance d, and if you measure the magnetic field, you can then measure how fast the charges are moving in a material. So you can learn about how fast the charges are moving by conducting this measurement of the Hall voltage. Here's a simple concept quiz to check your understanding. So here we have a current pass-through conductor as shown. Voltmeter is hooked up just like is shown in this picture, and it's measuring a positive voltage. I want you to tell me what are the directions of the Hall electric field and the magnetic field. So you have two possibilities for the magnetic field, into the page or out of the page, and you have two possibilities for the Hall electric field, pointing up or pointing down. Pause the video, see if you can answer this question before going further. So hopefully you have chosen one of these answers. Okay, the answer to this one, take it one at a time. I think the easiest one is maybe the Hall electric field. So notice that the way that this voltmeter is hooked up, the plus is to the top and the minus is to the bottom, and it's reading a positive voltage. So what that means is that the top surface, the thing connected to the plus, is 10 millivolts higher than the bottom surface. So that means the top surface is positive. Okay, positive on the top and negative on the bottom. And you know that electric fields point from plus to minus, so that means my Hall electric field, EH, must point downward, right? So I've got to eliminate this one and this one. Now I have to think about the magnetic field. So let's think about what's going on with a particular charge. Remember, this current is carried by electrons, so the electrons are moving this way. And how did the bottom surface get charged negatively? It got pushed downward by the magnetic force. So we know that the magnetic force must be pointing downward here, FB. That's how the bottom surface ended up becoming negative. So now think about it. If the force is downward, the velocities to the left what does the direction of the magnetic field have to be? Two choices, into or out of the page. It's going to be out of the page. Try it out. So try it with your right hand rule. My fingers of my right hand go in the direction of the velocity of the electrons, which is this way. Now, if magnetic field is coming out of the page, I need to curl my fingers in the direction of the magnetic field, which is coming out of the page. My thumb points up. But it's an electron, so I flip the whole thing over at the end, and I get a force downward, which agrees with what we want. You know it's got to be the opposite of the situation we showed here. Right? Here, the top surface was negative and the bottom surface was positive, and the magnetic field was going into the page. Here I have the opposite sign. I have the top surface positive, the bottom surface negative. The answer's got to be a different magnetic field than the one I had in the previous slides. Let me take a moment to talk about the directions of these, or the dimensions of this conductor. So I'm going to call L the length of the conductor. That's the direction along which the current is flowing. Okay, so L is always the direction along which the current is flowing. And that was the same thing we said when we were talking about resistance. R equals rho L over A. L was defined by the length, the direction along which the current is going. It's not necessarily the longest length. I could pass a current any of the ways in this conductor, and then L would be different. Okay, but in this case, the current is flowing this way. So that means my length is that long direction. Okay. I'm going to call T the thickness is the direction along which the magnetic field is applied. Okay, so T is this direction. And then I'm calling D is the other one. That's the one where the Hall electric field is being measured, or the Hall voltage. So make sure you understand L, T, and D, length, thickness, and D. So the length is the current goes along the length, the magnetic field goes along the thickness, and the other one, D, is the direction along which the electric field points. So we're going to use these variables going forward. Going back to the previous slide, I'm going to use this formula here. I'm going to pick up and continue to work with this one. Delta VH equals VBD. Okay, so here it is. That's the one that we worked out before, thinking about the balance of the magnetic force and the electric force. Now, if you think back to a few lectures ago, we talked about the current in terms of the number density, or the concentration of charges, the cross-sectional area, their charge, and their speed. I equals NQAV. So this is a formula which we derived before, relating the current to how many charges you have around and how fast they're moving. Notice that this A is this cross-sectional area here. Again, remember the current is going this way. So A is the kind of area through which the current is flowing. If you combine these two formulas, you can remove the drift velocity. So I can solve the drift velocity from equation 2 and plug it into equation 1. So in this step here, I removed the drift velocity, and I get this equation. Delta VH, IBD over NAQ. And we can simplify this a little bit more, because what is A? A is going to be equal to the product of D times T, right? So what I did in this step here is I substituted for A, thickness times D, and then I can cancel these out. So 1D on the top cancels with 1D on the bottom. I have this formula. The Hall voltage is IB over NQT. Also a very interesting formula because, for example, I can measure this with my voltmeter. I just read it off of the voltmeter. I can measure the current. Easy. I can measure that by reading it off of an ammeter. And maybe I can measure the magnetic field using a compass or whatever. And T is easy to measure. That's just the dimension, the distance I can measure with a ruler. And then I can learn about how many charges I have in the material, or the concentration of charges. I can learn, how dense are the charges that are flowing, carrying the current in the material. That's really, really interesting. I can learn about the properties of the material just by performing this Hall effect measurement. To finish this lecture, I want to do an example. So let's do this example, which is from an old final exam. A Hall effect probe uses a semiconductor with a charge carrier density of 1.75 times 10 to the 20 per cubic meter. And you're given the cross-sectional area of this probe. The dimension in the direction of the magnetic field is 0.25 millimeters, and you've got the current going through it. If its Hall potential is 5.5 millivolts, what is the magnetic field strength? And you're assuming that these are electrons carrying this current. So let's work this one out as the last step in this lecture. The application is from of this equation in the green box. So delta VH, the magnitude of that is I, magnitude of the magnetic field, over the concentration of charge carriers times their charge times the thickness of the semiconductor. So maybe try to reconstruct this diagram. Looks kind of like this. Remember, the current is going this way, I, so that direction then will be L, right? And the magnetic field is going in the direction of the thickness, so maybe I call it this, right? This is thickness. That means my magnetic field is along that direction. Maybe I'll put like my magnetic field is going here. And then the other direction is the depth D, and that's the direction along which the Hall voltage is being measured. So if I hook up my voltmeter like this, a plus and a minus, this is delta VH. So the Hall voltage is measured along the distance D, the magnetic field goes along T, the current goes along the length direction. So really, the only tricky part of this is the dimension in the direction of the magnetic field is 0.25 millimeters. That is T, that thickness. Remember, the thickness goes along the magnetic field. That's really the only hard part. And I got to solve for B. So solve for B. So we'll just put delta VH, N times Q times T divided by I is equal to the magnetic field B. And I know all these things, so I'll just plug in the numbers. So what is B? For the Hall voltage, 5.5 millivolts, so that's 5.5 times 10 to the minus 3 volts. Okay. N is given, 17.5 times 10 to the minus 3 meters to the minus 3. Let's write it like this, 1 over meter cubed. Times Q, that's the charge of the electron, 1.6 times 10 to the minus 19 coulombs, times T, which is 0.25 millimeters, that's 0.25 times 10 to the minus 3 meters, all divided by I, which is 4.5 milliamps, that's 4.5 times 10 to the minus 3. An amp is a coulomb per second. Good to check the units as always. So the coulombs cancels with the coulombs here. And one of these meters can cancel with one of these and it becomes a 2. What are the units of B? I have volts, I have 1 over meters squared, and then I have 1 over seconds. So that's volts, seconds per meter squared. This actually is a Tesla. This is a Tesla, so which is what we should have for the units of magnetic field. Okay, so one thing that I sometimes use is 1 Tesla is 1 kilogram per coulomb second. You can check that this is the same, right? Those are the same because a volt, remember, is a joule per coulomb. So let me go here. Volt is a joule per coulomb, and then I've got seconds per meter squared. And a joule is a kilogram meter squared per second squared times seconds over meters squared divided by a coulomb. And what do I have here? Meter squared cancels. One of the seconds cancels with this one. And I have kilogram per coulomb second, which is the same as here. Okay. So either way you do it, you find that the units of magnetic field are Tesla, which is what they should be. You didn't make any obvious mistakes. When I plugged the numbers into my calculator, I got 0.0 0.0856 Tesla. So there's the answer to that question. Now, always good to pause at the end of the day and say, is this reasonable? This is pretty reasonable. Remember, 1 Tesla is a really huge magnetic field. So if I had gotten something like 1,000 Tesla, that doesn't make physical sense. But this is really small, about 80 millitesla. That's reasonably could be created in the lab. Okay, so let me summarize this really important topic. If you have a conductor and you put it in a magnetic field which is perpendicular to the current, the charges are going to get pushed around. Because of that push, the charges are going to build up on one side of the conductor, and that creates an electric field which tends to counteract the force, the magnetic force on the other charges in the conductor. Eventually you strike a balance where the magnetic force is pushing them one way, but they're being repelled by the charges that are already there, and that gives you this equilibrium situation. And that happens when those two forces are equal. The condition for that is that the velocity of the charges is equal to the Hall electric field, which is developed by the separation of the charges, divided by the magnetic field. We got these two formulas here by manipulating this formula in the green box with some other formulas we already learned with current. These formulas can be used to measure things you don't know. For example, if I don't know the number density of charges in the material, I can use this formula to measure it. So that's a really, really interesting application. And this formula here can help you determine how fast the charges are moving in a material. So that's really interesting that you can get direct information about how fast the charges are moving by doing an experiment. I'm going to end it there. Thank you all for your attention, and I hope you've enjoyed this lecture, which really integrates the topics of electricity and magnetism and circuits together in this really important application of the Hall voltage. Thanks for your attention. Bye for now.